just attach the link of the attendance form for you all to fill up. Please fill it up now. And then the class code also given. You need the class code to fill out the attendance form. After a few more minutes, I will start the class. There are still some students haven't filled out the form. Please fill out now. Okay, there are 8 students haven't filled out the form. Okay, I have already give the instructions in the form there. The attendance need to be taken within half an hour after the class start. Okay, so make sure you fill out the form for those who haven't filled out. Okay, after I start the class, it's better you fill out now because I'm not sure later after I start the class, will be remember to fill it up. Okay. Y'all think I'll wait for a while. I will share to you again. Okay, 3 more students. Okay, so I will start the class now. Okay, today I'm going to finish the chapter 1. Okay, last week I have covered halfway on the VLSI design styles. Okay, I will recap on what is the design styles and then continue with the VLSI design flow and then what is the type of design type, okay, for IC. Okay, there are these topics that I will be covered. Okay, these are the topics that I will be covered today. Okay, hopefully in 1 hour I can finish all and then I will start with the chapter 2 on Wednesday. Okay, so we are SI design styles. You have your notes. Okay, you can refer to my PowerPoint here. Okay, these 4 design styles I have explained to all of you. Okay, not very details, but the very fundamentals knowledge about 4 of the design styles mentioned, which are the FPGA. Okay, FPGA. This is a few programmables. This one is what already? Gigate array. Okay, so FPGA in short we call it as FPGA. Okay, and another one is gate array design. Okay, this is the second design styles that are discussed last week. And the third one is the standard cell space design. And another one is a full custom design. Okay, so these 4 design styles, they need different times they require different design time. Okay, and then the cost is also different. Okay, and the applications, okay, for designing the IC using different design style is also different for these 4 design styles mentioned. Okay. Okay, so last week I have cover 4 of these, and then there are a table there that is for comparisons between these 4 design styles here. Okay, so I'm not sure whether you have started reading on the PowerPoint slide given to you. Okay, you can go and read during your revisions. Okay, now I will straight away goes to the table. Okay, because I stopped here last time. Okay, this one is the figure of the full custom. Okay, so I will start with this table. Okay, these are the comparisons of the design styles. Okay, the comparison here is made between the FPGA. Okay, let's have a look on the advantage of the FPGA. Okay, the advantages of using the FPGA is low NRE. NRE means that it is non-recurring engineering. Okay, this non-recurring engineering refers to the one-time cost to research, design, develop, and test a new product or product enhancement. Okay, so this could means the cost. Okay, the cost that including the research, okay, design and development, okay, of and applications. Okay, so means that FPGA require low cost, okay, for research. Okay, and then it is a fast time to market, means that from design to productions, it takes a very short time. Okay, so these are the advantages for FPGA. For gate array, gate array it require reasonable non-recurring engineering, means that it's the cost required is reasonable. Okay, not too high, not too low. Okay, and then the time to market as well. Can be short. Okay, depending on what is the applications what is the applications for design. Okay, and then moderate performance. Okay, moderate performance is the gates. The gates can be with 1 mega. Uh, okay, this is 1 mega gates, means that this is about 1 mega is how much? 1 million. Okay, 1 million gates. Okay, that are operated at 200 megahertz. Okay, and then good pricing. Okay, for standard cells, standard cells, if we want to use this standard cells design method to design the IC, we can achieve, we can make the IC to achieve highest performance. Okay, and then lowest volume cost, low power consumptions. Okay, and then using these design styles, the numbers of gate that can be uh, included in the design is roughly here given is 10 million. Okay, this is actually mega. Mega is 10 power of 6. Okay, but I mention it in million because million also 10 power of 6. Okay, so this is more gates that can be accommodated in the gates in the design. Okay, and then with higher frequency, which is 500 megahertz. Okay. Okay, and then the negative here for FPGA is the the applications, not applications, the IC can be with low performance. Okay, can be with low performance, high power consumptions, and high recurring costs. Okay, but for standard cells, and standard cells is a semi-custom design style. Okay, okay. Semi-custom is standard cell is a semi-custom design method. So the design time, if compared with gate array and FPGA, this is more longer. Okay, with longer design time. okay, with longer design time for standard cell, okay. And then the cost, okay, cost is also high, okay. The design cost is high, okay, because it is semi-custom design method. Okay, if these standard cells, we compare it with full custom, then the costs are even high. Okay, and then the design time for full custom is also very long if compared to standard cells. Okay, so these are the negative, the drawbacks for standard cells and full custom. Okay, so this one you have to understand. You have to understand the difference between all of these design styles, and then its drawbacks, and then its advantages. Okay, this is another chart. Okay, it's also about the comparisons for these four design styles. Okay, they are compared in cost and also performance. Okay, so here, okay, I start from this full custom design according to this chart here. Okay, the approach is extremely low. Okay, means that the design time is very slow. Okay, and then expensive. This is about cost. Okay, and then it is only used to design very high performance system. Okay, since a full custom design um, will require a very long design time. Okay, it is used to design a IC, okay, to perform a specific applications. Okay, so it can actually achieve a very high performance. Okay, depends on how we design it. Okay, so so for custom, this is the characteristic, okay, that you need to remember for full custom design. Okay, and then standard cell-based design. This approach is reasonable fast, okay, and less expensive. Okay, reasonable fast. This is when we compare it with the full custom design. Okay, if we compare it with the gate array based design, of course, the standard cells based design is slow. Okay, and so you must understand that here this approach is reasonable fast because it is compared with a full custom design and less expensive. Also the same. Okay, compared with full custom design. Okay, most ASIC are currently designed using this method. Okay, and then for gate array based design, this approach is fast and less expensive. Okay, ASIC performance are relatively slow. Okay, means that the performance is lower for the IC that is okay. This gate array based design, the performance uh, the performance of the IC is lower. Okay, for IC that is designed using standard cell based design. Okay, so for FPGA based design, the design process is very fast and cost effective. ASIC performance are slow. Okay, this shows slow. Okay, slow and also low. Okay, now I go to the next slide. Okay, okay, please stop me if you cannot understand what I mean here. And then sometimes when I talk, I didn't realize that I didn't realize I talk wrongly. Okay, if you get me not correct, okay, you can actually ask me and then to clarify. Okay. Okay, so this is another table. table that compares between the 4 design styles. Okay, the comparison is made on the cell size, cell type, cell placement, interconnections, design cost, area, performance, and fabricate. Okay, the cell size here, okay, what is meant by cells? Okay, cells here, okay, I'm not sure whether you still remember when you use the electric VLSI software, okay, to design a circuit. A circuit can be a logic gates, okay, logic gate like a NAND gate, AND gate, OR gate, inverter. Okay, you need to create a cell. Okay, that cell is actually represent a logic gates, okay, or a circuit. Okay, and the cells here we can actually, after we have complete it, we can place it, um, we can combine it with another cell. Okay, we can combine it with another cells. Okay, so okay, but here you just try to follow here. Okay, if you don't really understand, it is okay. Okay, but you just get the rough idea what is mean um, by the table here given. Okay, so for the standard, for the cell size, the cell size is variables for full customs. Okay, for the standard cells, it is a fixed height. Okay, get array, it is fixed, the size is fixed, and then FPGA, the size is of the cells is fixed. Okay, for the cell type, okay, cell type, it is variables for full custom, and then variables for standard cells, and fixed for gate array, and then it is programmables for FPGA. Okay, and then cells placement. Cells placements is in full custom, it is variable in full customs. And then in standard cells, okay, in standard cell, it is in row. Okay, and then the placement is as fixed for the gate array and FPGA. Okay, interconnections. Interconnections for the full custom design, it is variables, means that the numbers of interconnections it is variables. Okay, and then the standard cells, the interconnection also variable. Okay, and then the gate array, the interconnection is variable, and then for FPGA, it is programmable. Okay, the design cost for full custom is high. Standard cells is mediums, gate array is medium, and FPGA is low. Okay, for area, area here means the area of the chip die. Okay, this is the area of the chip die. Okay, if in a given chip, okay, the components that is to be placed in the chip can be compact. Okay, can be compact, and then uh, depending on how we design, okay, we can make it compact or we can make it um, uh, less compact. Okay, and then there is also, if the system is complicated, then the components that are to be fabricated on the chip will be more complex. Okay, so for full custom designs, the area will be compact. Okay, and then for standard cells, the area that it's occupied is compact to moderate. For gate array, it is moderate, and then for FPGA is large. Okay, and performance. Okay, performance. Okay, this one already mentioned just now. Okay, IC can be designed to achieve high performance if using full custom design. And then for standard cells, it also can design a IC with high performance and with also moderate performance. Okay, gate array is with moderate performance, FPGA is with low performance. Okay, and then fabrications. Okay, fabrications in full customs, all layers. Okay, all layers will be used. Okay, for fabrications. Okay, standard cells as well, all layers. Okay, gate array is to use the routing. Okay, this routing means the physical wire. Okay, this is about the physical wire. Okay, for FPGA, there is no need of fabrications. Okay, none. Okay, no need of fabrications because FPGA, the IC has already ready there. Okay, so we just need to design the program and then we download it to the IC to perform a specific task. Okay, so that is all about the comparisons between the design styles. Okay, now I goes to the another one which is about the design type. Okay, this design type is mean by what is the mode of this design. Uh, sorry, what is the mode of this IC? Okay, in operations. Okay, the modes here refers to whether it is digitals, analog or mixed signals via SI. Okay, mixed signals here means the IC can process both analog and digital signal. Okay, so this figure shows the ADC and DAC process. Okay, if the IC is operated in mixed signals mode. Okay, okay, this is okay. So I think most of you can understand what is meant by this diagram. Okay, this is the input. Input is an analog signal. Okay, these analog signals will be processed. Okay, to undergo ADC conversions. Okay, so after it has been converted to digital signals, there will be digital signal processings here in the middles. Okay, and then after process, if we want to output these digital signals, we need to convert it back to analog signal. Okay, so at the output here, okay, is the analog signals. Okay, here you see that there is amplifications, filtering, and etc. Okay, these processes are important. Okay, because if the signal is very low, we can actually amplify it. Okay, to restore back the signal. Okay, so that it can be used for different applications. Okay, and then some of the signals they are contaminated with noise. Okay, so there will be uh, the need of filtering. Okay, we need to filter the noise if the noise is in the signal. Okay, about mixed mode integrated circuit. Okay, this is about any IC that has both and processors of analog circuit and digital circuit on a single semiconductor die. Okay, on a single semiconductor die. In a real life applications, mixed signals design are everywhere. For example, smartphone and analog to digital converters are a mixed signal circuit. Typically, cost-effective solutions for building any modern consumer electronics applications. Okay, there are a few more applications that use a mixed mode IC. Okay, which are the wireless communications. Okay, wireless communications and also data converter. Okay, here already given analog to digital converter. Okay, and in additions, okay, the digital to analog converter also included. Okay, for smartphone, okay, smartphone here I want to specify here. Nowadays, all of us we use smartphone. Okay, and then the smartphone can actually uh, use with 3G, 4G, and 5G wireless. This is for wireless communications. Okay, 3G, 4G, 5G. This is the technology of the wireless communications. Okay, so all of this technology they use mixed mode IC. Okay, about digitals and analog. Okay, some of the devices they can process digital signals. Okay, some they cannot process digital signal, but they can process analog signals. Okay, but most of the devices they can process digital signals. Okay, why is that? Digital signals now is more easily processed by the digital devices. Okay, okay. The nowadays the digital system they are make it digital. Okay, because there are some of the advantages. Okay, here has stated a few. Okay, it is actually okay. Some of the advantages is not stated here. Okay, one of it is more uh, rubbish to the noise. Okay, means that the signals can be more immune to the noise. Okay, and then so as given here, the design time of designing a digital IC is very short. Okay, this is one of the advantages. Okay, and then okay, so for others, let me see. Okay, digital is regular, hierarchical, and modular. Okay, design at the design system level, standardized component must have a fixed value. Okay, simplified device models. Okay, so this is one of the advantages. Okay, if we want to design a digital IC, okay, the device model is more simplified. Okay, and available synthesis EDA tools. Okay, means that the tool is easily available. Okay, we can find the tools to design. Okay, the digital IC. Okay, design at the system level, first time successful prototyping. Okay, okay, so these are the some of the characteristic and advantages stated here for digital IC. Okay, for analog IC, it is irregular, hardly hierarchical, and it is designed at the circuit level, customized. Component must have a continuum values, require precision modeling, hard to find synthesis tools, mix bottom up, top down, longer design time, more spend for prototyping, difficult to test. Okay, less power consumptions. Okay, so this is the characteristic for analog IC. Okay, when we combine these two uh, for an IC to process means that if the IC is required to process both analog IC and sorry, if the IC is required to process analog signal and digital signals, then we call it as a mixed mode. Okay, so this is about classification of the circuit size. I have mentioned this before. Okay, so I will skip this slide. Okay, so all of you can understand this yourself. Now I goes to this traditional VLSI design flow. Okay, this VLSI design flow, sometimes we call it as VLSI design cycle. Okay, the VLSI design cycle starts with a formal specifications of a VLSI chip. Okay, follow a series of steps and finally produce a packaged chip. Okay, so this is the flow chart. Okay, shows the typical cycles. Okay, of a VLSI chip design. Okay, sometimes I call it steps. Okay, there are 8 steps here in this design cycle. Okay, system specifications, architectural design, functional design, logic design, circuit design, physical design, fabrications, packaging and testing. Okay, so what is meant by all this design before fabrications? I will mention each one here today. Okay, and then before we start to design, uh, the specification of the IC must be determined first. Okay, okay, these design cycles will go through when we have the specification of the IC to produce when we have a determines specifications of the IC to produce. Okay, so usually, okay, a customer, if a customer want an IC to perform a specific applications for his own product, okay, the customer can actually bring the specifications of the IC to a company. The company can be a semiconductor company that have that have expert, okay, to design the IC and fabricate the IC for the customers. Okay, so that's why the first things before design the IC, the specifications of the IC must be specified. Okay, must be determined and specified. Okay, here are the elaborations for each step of VLSI design cycles. Okay, so you have to remember the first step is uh, the IC. Okay, the system here means the IC. Okay, the specifications of the IC here means by system specifications must be determined first. Okay, so you see that the first steps of any design process is to lay down the specifications of the system. Okay, specifications is a high level representations of the systems. The factors to be considered in this process include performance, functionalities, and physical dimensions. These physical dimensions is about the size of the chip. Okay, and then after the specifications of the IC has determined, then next it will begin with the architectural design. Okay, this is this design is the basic is about to design the basic architecture of the system. Okay, the basic architectures of the system here include the decisions such as the RISC, okay, reduced instruction set computer versus the CISC. This is about complex instruction set computer. Numbers of ALU. Okay, ALU is the algebraic logic units. Uh, Algebraic, the pronunciation. can't remember well. Okay, arithmetic. Okay, this ALU is a unit that perform calculations, okay, mathematic calculations. Okay, so on the IC, this one have to consider. Okay, and another is floating point units, numbers and structures of pipeline, and signs of cages, among others. Okay, this is a general descriptions for architectural design. Okay, next is about functionals and behavioral design. Okay, the main functional units of the system are identified. It identifies the interconnects requirements between the units, the area, power, and other parameters of each unit are estimated. The behavioral aspects of the systems are considered without implementation specific informations. The key idea is to specify behavior in terms of input, output, and timing of each unit without specifying its internal structures. Functionals, Functionals design provides quick emulations of the systems, allow fast debugging of the full system. Behavioral design is largely a manual steps with little or no automation help available. Okay, so as you see that functional design is also means as the behavioral design. Okay, in behavioral design, so we can write the IC. Okay, we can write the functionality of the IC in behavioral way. Okay, means the behavior of this IC. Okay, and then how it is designed to perform specific operations. Okay, so as you see in this figure here, if we want to write the IC, the behavior of the IC, or the behavior of the circuit in the IC, we can write it in this way. Okay, this is this is the descriptions. Okay, the behavioral descriptions that use the VHDL. Okay, hardware description language to describe the circuit. Okay, after the functional design is complete, okay, normally it will need to be verified, okay, and then to check the error, okay, to check whether the circuit can perform correct operation as required or not. Okay, if the operations of the circuit is correct, okay, then we can proceed to the next design. If not, then the circuit need to be corrected. Okay, the descriptions of the circuit need to be corrected and then verified again. Okay, so the next design after the functionals design is logic design. Okay, logic design, the control, okay, during logic design, the control flow words, reads, register allocations, arithmetic operations, and logic operations of the design that represents the functionals design are derived and tested. Logic design is performed at the registers transfer level RTL using a hardware descriptions language HDL by means of programs that defines the functionals and timing behaviors of a chip. Okay, two common HDLs are Verilog and VHDL. Logic synthesis tools automate the process of converting HDL using high-level synthesis tools to test and verify its correctness into low-level circuit elements, okay, to achieve a smaller logic design which conforms to the functionals design. Okay, after functionals design, so the circuit, okay, can be convert, okay, and also tested in a logic design. Okay, so logic design we usually call it as RTL design. Okay, sometimes we call it as RTL design. Okay, this RTL design also use the HDL language, okay, to write the code. Okay, and then it will also need to be verified of the correctness of the circuit, okay, the operations of the circuit. Okay, so after we verify it, okay, this is RTL simulations. Okay, RTL simulations, and then followed by the logic simulations. Then after that, the next design is to verify the circuit at a circuit level. Okay, so for the bulk of the digital logic on the chip, the logic synthesis tools automatically convert the Boolean expressions into a gate level netlist. The Boolean expressions are converted into a circuit representations by taking into considerations the speed, power requirements of the original design. Circuit simulations such as a SPICE is used to verify the correctness and timing of each component. The circuit elements, cells, macros, gates, transistors, and interconnections between these elements are expressed in the circuit design. This representation is called a netlist. Okay, elements designed at the circuit levels are static, RAM blocks, input-output, analog circuits, high-speed functions, and etc. Okay, so after the IC, okay, the design of the IC is verified at a circuit level. Then the circuit can be sorry. There is another design. Okay, just now I want to say after the circuit design, okay, it can be fabricated. Okay, but I just remember that there is another design which is the physical design. Okay, there are one more design which is the physical design. Okay, physical design is about designing the IC in a layout form. Okay, so this is the circuit design. Okay, so all these are the transistors. Okay, they are CMOS transistor or BJT transistors. Okay, at circuit design. And then after this circuit design, we need to perform physical design. Okay, so this is the physical design. Sometimes we call it as a layout design. Okay, you learned this before. Okay, in this step, okay, so follow to these statements here. In this step, the circuit representations or netlist is converted into a geometric representations. These geometric representations of a circuit is called a layout. Layout is created by converting each logic components into a geometric representations with a specific shapes and appropriate routing, connections in multiple metal layers, which perform the intended logic functions of the corresponding component. Connections between different components are also expressed as geometric patterns, typically lines in multiple layers. The exact details of the layers also depends on design rules. Okay, after complete the layer design, we need to verify this design based on the design rules that is defined in the software. Okay, after it passed the design rules, okay, we need to perform others checking as well. For example, ERC. Okay, ERC is to check the well. Okay, and also we need to perform others check. For example, antenna check. Okay, this one depends. Okay, not all design need to perform this antenna check. Okay, and then after the layout design has passed all the checking, then only it can be stimulated using the SPICE to verify the operation circuit. Okay, the circuit operations. Okay, so after the layout design has verified correctly, then it can bring to fabricate out the real IC. Okay, so the description is given here. After layout and verifications, the design is ready for fabrications. Layout data is converted into photolithography masks, one for each layer. Masks identify space on the wafer where certain materials need to be deposited, diffused, or even removed. Silicon crystals are grown and slide to produce wafers. The fabrication process consists of several steps involving depositions and diffusions of various materials on a wafer. Okay, so this is about the fabrications. Okay, in the next chapters, chapter 2, I will elaborate more on the fabrication process of an IC. Okay, after fabrications, okay, the final steps will be packaging, testing, and debugging. Okay, finally, the wafer is fabricated and diced into individual chips in a fabrications facility. Each chip is then packaged and tested to ensure that it meets all the design specifications and that it functions properly. Okay, so this is an overall descriptions for all the steps in the VLSI design cycles. Okay, I have one slide added here into my PowerPoint. So in the notes given, the notes given is the one that I have uploaded to you in Google Classroom. You will find that there is no this no the there is no slide. Okay, this slide is not included in the notes given to you in Google Classroom. Okay, because I have just updated last night. Okay, so this one I will update again. Okay, I will upload the latest one to you so that you can refer to this slide. Okay, why I update, I add another slide for this. Okay, because you see that okay, VLSI design flow. Okay, they if you see in the website, different website, they give a different design flow. Okay, I included here because I want to clarify to you what are the difference and then how do we understand the design flow given uh, if it is not given in this uh, in this way. Okay, So the one that I give you here, it contains architectural design, functional design, logic design, circuit design, and physical design. But you can also find another design flow which is only given on which is not given with the architectural design, functional design, logic design, and circuit design. Okay, but they are elaborate in another way. Okay, so this is another design flow. Okay, that is also valid. Okay, that is also valid. Okay, this flow chart explain all the design given here. Okay, so this is for you to know which one to study. Okay, if you find a design flow look like this, okay, it is also correct. Okay, because all this is about the design part for this. Okay, so as you see that in this design flow, okay, it starts with design specifications. Okay, and then behavioral descriptions, okay, and RDL descriptions. Okay, so these two behavioral description is actually for the architectural design. Okay, and then for RDL descriptions here, this is for this is covered for the functional and logic design. Okay, functional and logic design is actually means by this RTL design. Okay, here given as RTL description, it is actually about RTL design that use the hardware language, okay, HDL, to describe the operations of the circuit. Okay, after the design is complete, then we need to perform functional verification and testing. Okay, just now I have already mentioned. Okay, if the operations of the circuit is not correct, then it need to be corrected and then re-verified. Okay, after the verification is done successfully, then it will need to perform logic synthesis. Okay, to perform logic synthesis, this is to use the a synthesis card tools, okay, a computer's added tools to convert the RTL design to perform the logic testing, okay, on the design. Okay, and then this logic synthesis, it is also about to use the CAD tools, okay, to convert the RTL design to get level netlist. Okay, get level netlist. This is this circuit design. Okay, get level netlist normally contain the list of the port, pins, cells, and routing. Okay, so after the netlist is obtained, then it can be used to perform logical verification and testing. Okay, after this is done, then straight away can goes to this physical layout. Okay, this physical layout is about physical design. Okay, for this floor plan automatic place and route, okay, this one is under physical layout. Okay, but for this flow chart, it is placed before the physical layout. Okay, but it's okay because here as given there is an error. This error shows that after the physical design, it can be verified. Okay, after verified, if it is not correct, okay, it needs to perform the checking again. Okay, so for physical layout, okay, I know that it's almost time. Okay, give me a few more minutes and then I will end the class. Okay, so this one physical layout. Okay, I want to show you the previous one, the flow chart here. Okay, so this is the physical design. Okay, under physical design, there are a few more steps. Okay, that have to be followed. Okay, which is the partitioning, floor planning, placement, clock tree synthesis, signal routing, timing closure. Okay, so just now the one that is about floor planning, um, and route. Okay, place and route. Okay, is actually under this one. Okay, is under this one, under the step that is under physical design. Okay, so this one I will cover in chapter 4. So I'm not going to explain in details today. Okay, so this is what you need to understand, the meaning and the relationship of the design given here. Okay, these are the process that must be followed if we want to fabricate an IC, okay, an ASIC, a specific application specific IC. Okay, so this is the end of chapter 1. Okay, is there any questions so far? Okay, I guess no questions. Okay, always no questions from you all. Okay, maybe when you do your revisions, you will find you will have questions. Later, you still can ask me back. Okay, so we still have a tutorial class later, okay, for the second group. Okay, today the tutorial class is for group 2. Okay, group 1, I will make a replacement class, okay, later. But your turn will be next week. Okay, so today is group 1. Sorry, today is group 2. Okay, so we can dismiss class now. Okay, before that, let me check again the attendance. Okay, so all of you have filled out the attendance. Okay, no problem. So we can dismiss class now. Thank you. Okay, for those who will be having tutorial with me, you need to stay back.